Okay, some of the questions I asked you to try last week, okay, last 2 weeks. Okay, today I will discuss the solution. Also, I will need you to check your answer. Okay, if you get a different answer, you can show me. Okay, and then you can ask if your answer is correct or not. Okay, but okay, now let me see. I need to go to washroom for a while. Okay, is that okay if I discuss the solutions with you after I come back? Okay, during this time, maybe you can try other questions. Okay, if you haven't finished, you can continue. Okay, if you have already finished, then you just wait me for a while. Okay, now I will start to discuss the answer with you. Okay, in tutorial 3, there are 3 questions. Okay, I ask you to try. Okay, question 1C, 3A, and question 6. Okay, I want to ask, I cannot remember. Question 1C, have I discussed with you before? I remember I have discussed it, but I am not sure. I want to confirm again. Okay, yes. Okay, so I will skip question 1C today. Okay, I have discussed it with you. Okay, now I goes to question 3. Okay, 3A. Okay, so question 3A is about to sketch a transistor level schematic and stick diagram for a compound CMOS logic gates for each of the following function. A equals to, not equals, A, in part A is Y. Okay, Y equals to A product with B and product with C, and sum with D and with a bar. Okay, so the solutions here, okay, this is my solution. Okay, you can check. Okay, but this solutions is not only one solutions. Okay, your solutions might be different. Okay, you can check with mine first. I will explain based on my solution here. Okay, so for how I get this. Okay, how I draw the transistor level schematic and the stick diagram. Okay, so for this one, the Boolean functions that we use is this one. Okay, I cannot, can I write anything here? Okay, since I cannot write, okay, now I'm using PC. Okay, I'm using the PC in the classroom. Okay, there's no features that I can write here. Or can I can write. Okay, so we should get a Boolean functions for PMOS and NMOS. Okay, you see here, this is the two Boolean functions for the pull up and pull down network. Okay, so to draw the schematic diagram, we can use the Boolean functions to draw it. Okay, this one for the pull down network, I get it as a y bar equals to a b c, sum with the d. Okay, so this one, okay, I think all of you are familiar now. You have started to get familiar how you should draw the schematic. Okay, for this one, when all operation, okay, when all operation means it is in parallel. Okay, in parallel. Okay, and operation, it is in series. Okay, so here A, B, C, this is all. Okay, this is N. Okay, so we should draw it as A, B, C is in parallel. Sorry, I get it wrong. This is N, this is all. Okay, this is N, this is O. Okay, plus is O operation, product, this is product. Okay, ABC is the product. Okay, this is N operation, so it will be in series. So you see here, ABC is in series, and then it is in parallel with D. Okay, this is for the pull down network. Okay, let me change to another color. This color not nice. Okay, you cannot differentiate. Okay, now to draw the PMOS, okay, to draw the PMOS, you can draw it accordingly. ABC is in series. So in pull out network, then it will be in parallel. So you see ABC is in parallel. Okay, and then this configuration, okay, will be in series with D. Okay, this is in series. This is series. Okay, the configurations must follow in this way. Cannot terbalik. Okay, if this one, these configurations you draw it in pull-out network, then means it is not correct. Okay, must follow this way. Okay. Okay, if you draw the schematic, it's not like this. It's not exactly like this, but all the configurations are correct. Or what I mean is, if you draw it this way, you have this A, B, C is at the bottom here, and then D, the transistor with input D here is at the top. Means like this one. This is D. Okay, I think most of you can get what I mean here, right? Okay. I want to draw it to show you, but seems like quite difficult here to draw because of the limited space. This is D. Okay, this is, okay, I roughly sketch, okay, to show you what I want to, what I mean just now. Okay, this is B, this is A, this is C. Okay, so if your pull-up network is something like this is also considered correct. Okay, but when you determine the Uri path, maybe they are of the same Uri path or maybe different. Okay, we can get the same one. Okay, even though these two, the positions here are, uh, the positions here change. Okay. Okay, this one also, if here is A, B, C and here is D is also fine. And if the transistor, the sequence of the transistor change here, okay, if let's say this is A, B, C, okay, the sequence here is different, also correct. Okay, but when you get the Uri path, the Uri path maybe will be different. Okay, so for this one, this is the schematic that I will use. Okay, the schematic, based on the schematic, okay, the Uri path that I am able to determine is DABC. Okay, DABC means the Uri path is like this one. D, A, B, C. Okay, there is a note here. They should look like this, something like this. Okay, this is A, B, C, this is D. Okay, and then this UV path, okay, must be the same also in pull down network. Means that in pull down network, the sequence of the transistors, must be the same with this DABC. Okay, so here if to check, okay, it should start at this node, okay, and then go through the transistor with input D. No, sorry, so this is not correct. Should not start at this node because this is D to A. Okay, if I start at this node, it is going from D to C, okay, not D to A. So means the relay path should be from other node. Okay, it should from other nodes, should from this node. Okay, and this node then should go to this node. Okay, passing through the transistor with input D, and then goes to a transistor with input A, B, C, then back to this node. So this one will be the correct. Okay, this is the correct one. Okay, so there is 3 nodes here, as you see. Okay, this is the node. Okay, when you draw the Euclid path, you need to determine the node first. Okay, so after you determine the nodes, you can draw this. Okay, you can draw the Euclid path like this. Okay, so this is the Euclid path. Okay, this Euclid path is not just only one Euclid path. It can be more. Okay, the Euclid path that to identify must be the same in both pull-up and pull-down network. Okay, and then the Euclid path must be of the same directions. Not same directions, but it's only in one directions. Okay, it must be in one direction, so it cannot be reversed. Okay, so after we determine the Euclid path, okay, then we can start to draw the stick diagram. Okay, so this is the stick diagram. Okay, with the order of the Euclid path that is based on the Euclid path of 10. Okay, D, A, B, C. Okay, now we should label, okay, the drain and the source terminal. Okay, drain and source terminal. Okay, we need to label so that we can draw the connections, all the connections correctly. Okay. Okay, so you see here the source terminal. Okay, how to determine the source and drain terminal in stick diagram? Okay, in here you see here this is the connections. Okay, that is with the contact to VDD. Okay, and here the terminals is labeled as source terminal. Okay, it is best that we minimize the number of connections. If we can make them to one similar terminal, that is to the one to the VDD, then we should make it that way. Okay, if we label this as source, this is as source, and this is drain. Okay, it is actually not correct. Okay, we will find that it is quite difficult to draw the connection. Okay, so the source will be here. Okay. Okay, based on the schematic diagram, okay, I refer to my own schematic diagram. Okay, the schematic diagram here, the A, B, C source terminals are connected to the VDD. Okay, here A and B are adjacent, so the terminal here should be labeled as source. That is connect to the VDD. Okay, and then here also another source terminal connect to the VDD. Okay, after we label the source terminal, and then here we know that it is a drain terminal. Okay, okay, we can label others terminal as well subsequently. This is drain, okay, drain, and this is source. Okay, how do we know this is source? Okay, we have to refer back here. Okay, the drain terminals of the transistor with input A, this is drain terminal, is connected to the source of the transistor with input D. Okay, so this is D. If you determine here the transistor as drain current, it is not correct. Okay, it should be source because it is connected to the drain terminals of the transistor with input A. Okay, and then here, the drain here, since this is source terminal, so this will be the drain terminal. Okay, so after we label all the drain and source terminals, then we can draw the connections. Okay, all the connections must be with the contact. Okay, the cross is the contact. Okay, so for this one, you see this two contact. Okay, is actually this one. Let me see. Okay, it's actually this part. You see there are four terminals are connected together. Okay, four terminals are connected together. You see here, this is the part where this terminal is connected to this terminal. Okay, and then here D, this is drain terminals for both transistor with input B and C. So means here, okay, at this node there are four connections, okay, from four terminal. Okay, so it should be uh, it should be drawn in this way. Okay, these two terminals they are connected, and then they are also of the same node of another terminal. So that's why you see here this contact and this contact they are connected to this. They are connected together. Okay, through the two contact. If we didn't draw this contact with these connections, means your stick diagram is wrong. Okay, so you need to make sure that you understand all the connections here and then you draw all in the stick diagram. If you miss any of the part, your stick diagram we consider incorrect. Okay. Okay, so this is on the pull-up network, and then now pull-down network. Okay, pull-down network is very easy. Okay, it is easy because the connections here we can directly know. Okay, how to draw out the connections. Yes, the source terminals of the MOS all are connected to the ground. Okay, and not all, but only two transistors here. Transistor with input C and D. Okay, so we can determine the connections here. Okay, you see this is D and C, right? Okay, they are not adjacent. Okay, since they are not adjacent, so we cannot draw the connections together like this one. So we have to draw the connection separately. Okay, so one is here. This is the source terminals. Okay, draw to connect to the ground, and this one also. Okay, and then others is we have to connect it to the output at this node. Okay, you see here there are three transistors A, B, C. Okay, they are in series. Okay, so nothing we should do. Nothing. There is nothing we need to do to draw in series. Okay, they are connected. Okay, automatically connected like this. Okay, except that the drain here, drain terminal are connected to Y. Okay, here the drain terminal is the drain terminals of the transistor with input A and D. Okay, so this is A and D. Okay, with two drain terminal, so we need to draw a contact. So this contact is used to make a connections to the output Y. Okay, so you see this is how the drawing should look like. Okay, so you see the pattern of the stick diagram in series and in parallels. For any transistor is in series, you see here A, B, C. They are in series. They look like this. Okay, but if in parallel, the connections must use the contact to connect to each other. Okay, so if you want to check your stick diagram, this is how you should see. Okay, any issue on getting the answer for these questions? Okay, this is all my explanations on the solutions for these questions. Okay, I believe all of you have learned and then you know how to draw the stick diagram. Okay, since all these you learn in the lab, okay, you need to include it in your lab reports. I assume that now all of you can draw the stick diagram and then you also understand how the concept here. Okay, due to limited time now, I goes to the next questions. Okay, the question 6. Okay, this question also quite important. Okay, this one I need to rough. Okay, this is my answer. You can refer as well. Okay, question 6. Consider the transistor level schematic in figure 1 below. So figure 1 is sorry, this one is not a transistor level schematic. This is a stick diagram. So there is a problem here. No problem. Okay, there is a corrections that you need to make. This is a stick diagram. Okay, is the question correct? Let me check again. Okay, here is correct. Okay, this is in my solution. Okay, so this is a stick diagram. In part A, okay, the functionality of the Boolean functions have to determine and then sketch the transistor level schematic. Okay, to determine the Boolean function. Okay, how to determine? Okay, if you find that you feel difficult to draw the Boolean functions from the stick diagram, you can draw the transistor level schematic. Okay, after you draw this, then you can directly define the Boolean function. Okay, so this is how the Boolean, not Boolean, this is how the schematic should be drawn. Okay. Okay, to draw the schematic, first we need to identify the source and drain terminal as well. Okay, if we don't want to determine the source and drain terminal, it is also okay. You can directly draw out. Okay, we can know. Okay, here is the source. This is drain. This is drain. Source. This is drain. This is source. Drain. Source. Okay. So here, why it is here source because it's VDD. Okay, so this transistor with input A. Okay, the source terminal is connected to VDD. So here A, the transistor here, the source is connected to VDD. Okay, and then the drain terminal of A is connected to this source terminals of B. So means that this is D, this is S. Okay, this is drain terminal, this is source terminals, and this is drain terminal. Okay, and this drain terminals is connected to this drain terminal of another transistor. Okay, so this one is with input D. Okay, so this one is D, this one C, D, and source. Okay, there is some error here. There is one error. Can you identify what is the error here? Can you tell me? I will need you to tell me. I know where is the error, but then I want you to identify and tell me. Okay, this schematic is not consistent with the stick diagram draw. Okay, it's not consistent. Okay, why? There is an error here. Where should we make the changes in the schematic? D then C, sequence of D and C in put-out network. Yes, correct. Okay, you are right. So here, the sequence here, this one is D, this is C. Okay, so this one is the correct one. Okay, okay, and then in pull down network. Okay, now pull up network already settled. Okay, now pull down network. Okay, pull down network also we need to determine the source and drain terminal. Okay, so for this one, this is source, this is source. Okay, here is drain, this is drain. Okay, this must be drain. Okay, why here must be drain? Because the terminals are connected to the output. So we should label here as drain. This is source and this is source. Okay, after we label, then we straight away we can draw out easily. Okay, the label of source and terminal is actually quite important so that you can easily identify and also draw out the correct schematic. Okay, so for this one, this is AB. AB, this is source, right? Okay, looks like my schematic of the pull down network is also not correct. Okay, so this is source. Okay, means that this should be A, this should be B. Okay, why? Because here the source terminal are connected to the ground. Okay, and then drain terminal here, two drain terminals. Here they are drain terminals are connected to the source terminals of C. Okay, so this is okay, just now here this is A, right? This is C and D. Okay, so here the source terminal is to the C transistor with input C. Okay, and then also connected to the source terminals of the transistor with input D. So it's at this node. Okay, this one should be the correct one. Okay, and then the drain terminal of the input C of the transistor with input C and D should connect to the output. So it should be this one. Okay, so this is how we should draw the schematic. Okay, after we draw it, then we can determine the Boolean function. Okay, A and B is in parallel, so means that A and B are in all operations. So A and B, you see this is all operations. C and D also in all operation. Okay, so these two are in series. These two are in series. So you see this is an AND operation. Okay, this is for pull up network. Okay, in pull down network, we can provide it this way. Okay, so you should provide this one, but if you give this one, I also will consider it as correct. Okay, this is for part A. So now I goes to part B. Okay, part B is to sketch the layout design diagram. The dimensions of the layers in the layout must follow the scalable CMOS as given in table 1. Okay, so this is the layout design. Okay, this layout design must follow this stick diagram. Okay, if you don't want to follow, it is also okay. But since the stick diagram already given to you, then you should follow this stick diagram, or else you will take more times to find out another ULIP path and then to draw another stick diagram, uh, and then you draw and then you draw the layout. Okay. Now the layout you can straight away use the stick diagram given to draw it out. Okay, and then the sequence of the polyline is also the same, A, B, C, D. Okay, so here all the layers must be mentioned, okay, with their width and spacing according to the MOSIS design rules given in table 1. Okay, so you see this layout design, you see this layout design, okay, all are with the metal polyline layers, okay, and then the anvil diffusions area. Okay, the width here for the diffusions area, anvil, and then the polysilicon line and the metal layer are all mentioned. Okay, okay, the table here, okay, according to the table given, okay, this is the table 1. Okay, in this table, there are scalable CMOS and submicron and deep rows. Okay, the question asks you to use the scalable CMOS, so it will be this first column, the first column here. Okay, so all the width and spacing are already given here, just that you need to know uh, how to label accordingly. Okay, for example, width of the polysilicon must be 2. Okay, so in your drawing, okay, you need to label the width of the polysilicon as 2 as well. Okay, so this is 2. And also for metal 1, the width here, okay, we also need to determine. According to the table here, metal 1, the width is 3. Okay, for contact is 2 by 2. Okay, so the contact here, you see here, I enlarge the drawing. Okay, this is the contact. That is in black color. Okay, so 2 by 2. And then you see here, the diffusions area here is 3. Okay, okay, for this one, I want to explain a bit. Okay, refer back to this table 1. for the diffusions area, the width is 3. Okay, this is the minimum width, which is 3. Okay, so that's why just now in drawing it is stated as 3. Okay, but we can also mention it as 4. Okay, we can draw it, we can state the width as 4 as well. Okay, or 4. Okay. Okay, why I say that, why I mention this? Okay, because some of the rules you will see that the contact here is 2 by 2, and then there is another measurements here. This is 1, this is 1. Okay, I mean here. Okay, this is 1. Okay, 1, 1 plus 2, this is 4. Okay, if you draw this one as 1, 2, 1, okay, and then the diffusions area is 4, I also consider it correct because the minimum width for the diffusions area is 3. So it's, if it is above 3, then still okay. Okay. And then for others as well, others, whichever you can identify, you need to label here in the layout design. Okay, I see it's almost time, but let me finish the part C. I will quickly discuss the part C. Okay, then later only we end the class. Okay, so part B, no problems, right? Okay, I will quickly go to part C now. If any problem, then later you let me know. Okay, part C, we draw the layout if the feature size is set to 2 lambda in the process, where lambda is equals to 0.6 micrometer. Okay, there is a corrections here I want you to make. Okay, here lambda equals to 0.6 micrometer. I want you to change to 0.3 micrometer. Okay, why I need you to change this to 0.3 micrometer? It is because the layout design that you draw based on lambda, okay, I want you to refer to this one. Okay, this one is the one that I give you in your lecture, in the lecture notes. Okay, I give you in the lecture notes, and then this, the lambda is 0.3 micrometer. Okay, I don't want to confuse you because some of the lambda, okay, the values given is different. Okay, and then the lambda rules here that is applied to the width and spacing is also different. Okay, for this one, it is 0.3 micrometer. Okay, this one, make sure that you change it to 0.3 micrometer. Okay, I'm not sure so whether you have solved this question, but these questions, if you refer to the lambda design rules, you can use back this layout design, and then you determine each of the width and spacing. Okay, so my answer here is like this. Okay, I refer to this one, the lambda rules here given in the lecture notes. Okay, the polyline, the width is 2 lambda. Okay, why 2 lambda? Because here given is 2 lambda. Okay, and then the contact, this is 2 lambda by 2 lambda. Okay, and here also you see it is given as 2 lambda. This is, okay, 2 lambda by 2 lambda. Okay, this is already mentioned here. Okay, and then metal 1 diffusions contact. Okay, this is 1 lambda. Okay, the 2 lambda, the contact is not only on metal 1 to polysilicon, it is also on metal 1 to the diffusions. Okay, the contact. Okay, so that's why it is labeled as this way. Okay, and then here also this is the extension of the polysilicon. Okay, 2 lambda. Okay, it is referred to here. Okay, and also other dimensions is the width of the diffusion area. This is 4 lambda, and also the spacings between the diffusion. Okay, this one I refer to this one. Okay, I refer to this one. And also metal one here, the width given is 4 lambda. Okay, this is 4 lambda. So you need to also label the metal one, the width of the metal one. Okay. Uh, okay, so this is the solutions for all the questions in question 6. Okay, there is an additional materials that I have uploaded to you. Okay, the materials that I mentioned is this one. Okay, this is on the, the layout design rule is an additional handout like I give to you. Okay, this one you can refer. Okay, why I give you, because you see here all the dimension and spacing between the layers. Okay, sometimes when we see the descriptions here, we don't really understand what does it mean. Okay, here there is some of the drawings that is a draw. Okay, so based on the drawing here, you can always know what is meant by all the dimensions given here. Okay, so you can refer to this material, okay, for you to understand what is meant by the meaning, like for examples, the get extensions out of active. Okay, this is 2. Okay, means here this is the gate. Okay, the poly gate. Okay, that is extend out from the active region. So this is mean by the drawing here. Okay, others as well, you can read carefully and then you refer to the drawing here, maybe can help you to understand what does it mean. Okay, and then the first page here, this is about the lambda rules. Here the lambda given is 1 micron meter. Okay, the question I gave you, the lambda is not 1 micrometer. So remember, don't refer to this one because the measurements here may not be the same. Okay. Okay, so this is all about the discussions of the tutorial solutions for today. Okay, so I think I should stop and end the class now because I see that now it's already past 12:30. Okay, let me check your attendance first. Give me a minute. Okay, so no problem. I received all your attendance form. Okay, if no further questions, then we can dismiss class now. Thank you.